Today I'm going to talk about determining the resistance of a cube. And we are going to create the following structure. We have a cube. Yeah, like our typical cube. Right? And this cube, you can probably make them continuous. Has edges, and all these edges have the same resistance. They all have resistance R. So those four, all resistance R. There's resistance R here, resistance R there, 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 there. R is everywhere. And then we're going to feed in a current I. Yeah. Through some voltage U, and we're going to take it out here. Yeah? So we're going to feed it in here, we're going to take it out there. And the question is, what will be the resistance when you look inside at this point? So if you remove the cube, what resistance will the cube have if you feed it with a voltage U and a current I? Right? So we will see that the resistance, the total resistance, equals U over I. So that's what we need to calculate. What is RT? Now, if we look very carefully, this looks very symmetric. And according to Kirchhoff, there will be currents running here. There will be an I1, there will be an I2, and there will be an I3. So we can say I equals I1 plus I2 plus I3. We can say that. Yeah? And since it is totally symmetric, from this point, the circuitry here looking inside looks exactly the same as here, looks exactly the same as here. So these currents will be the same, right? So you will get I1 will be the same as I2, will be the same as I2, will be the same as I3. Now we are at this point. Again, the current will be split up in two pieces, right? I1 will essentially be I4 plus I5, which is I4 here, for instance, and I5 here. But again, due to symmetry, these currents will be the same. This one and this one will be exactly the same. Yeah? And it will essentially be half the current from what you have here. Right? So, what you could say is that I4 is essentially a half I1. Right? And I1 is again a third, because of the symmetry, of I. Right? So here you have a third of I running everywhere. So there will be a third I here, there will be a third I here, and there will be a third I here, right? Let's write this in front. There will be a third I running here. That will again be split up in two pieces, so you get a sixth of I running here. So I4 will be a sixth I, and I5, yeah, will also be a sixth I. Right? So now we know the current running through here. We know the current running through here, which is a third I. What will the currents be here? Well, you can look at it from the other side. We expect that I will be there also because of Kirchhoff, right? Current is conserved. So here you will also have a third I running. And here you will have a third I running. And here you will have a third I running also. Right? Here, here, and here. All these branches will have a third I. So now you can very simply add up all the various voltages, get it to U, and you can calculate your resistance. So let's do that. So you have a third I running here times R. So the voltage drop on this resistance with these two terminals here equals a third I. So the total voltage between this point and this point is made up of this voltage plus this voltage plus this voltage, right? So you have here a third IR from this one. Here we already said it was a sixth, so you do a sixth IR here. And then again you have a third IR here. So you add that all up and you get 5/6 IR. And that gives you the overall result, the total resistance now, R, right? Oh. The total resistance, R total, which is U over I, equals 5/6 IR, this one, that's the U, divided by I, equals 5/6 R. So the resistance between this terminal and this terminal, if you would measure it, it's really 5/6 R. So R total equals 5/6 R. Now I think this is an excellent place to stop. If you like this video, please like and subscribe, and I'll see you in the next.